Hello, my name is Chris Eliasmith, and I'm co-CEO of Applied Brain Research. And I also hold a chair in theoretical neuroscience at the University of Waterloo. It's a great privilege to be speaking to you today as part of the inaugural Brain-Inspired Computing Congress. Of course, no one expected COVID for our first year, but maybe that'll make it more memorable. Anyways, today I'm going to talk to you about neuromorphics. This is a field that many of you have no doubt heard of, but might have very different ideas about exactly what it is. And I'm definitely not going to sort that out, but I will go over a history of the field, recent advances in neuromorphics, and a comparison of neuromorphic AI to non-neuromorphic AI in order to draw some conclusions about what the future holds for the field. But before doing that, let me start with why neuromorphics is exciting to begin with. So when we look at mammalian brains like ours, we notice that communication looks quite unique. We see these stereotypical spikes of voltage, and those correspond to messages being sent. It's pretty tempting to think of these as ones, which is not too far off, but it's really missing a critical factor. In particular, we'd be missing that these spikes, the ones, are happening at a specific moment in time. That means the output of the neuron isn't just a function of the input, and you can actually see the input in this movie at the top here. So it's not just a function of the input, it's a function of that input and of time. You'll notice that the spike density here changes with this constant input. If you think about standard neural networks, their output does not depend on time like this. And I'll come back to this point later, but for now, the important thing is to notice that this temporal processing means the brain is driven by events. And what this means is that you don't expend effort and energy if there isn't something to do. So people soon realized that biology is incredibly energy efficient, as you can see from this graph on the right. Biology is way down here at the bottom. And I don't mean it's kind of energy efficient. It's several orders of magnitude more efficient than our best computing substrates. There are several things to note on this graph. The first is that we've gotten a lot more power efficient since the 70s, right? So we're already down around here, and in the 70s, we were way up here. The second thing to notice is that there's a wall for 32-bit processors. So it doesn't seem like we're going to be able to get much more efficient than this for really high precision computing. Third, there's a lot of room between that wall and the efficiency of a biological neuron, of about 8 orders of magnitude. That means you could take a processor that runs for 1 second on a battery, and if you improved its energy efficiency by 8 orders of magnitude, it would then run for 3 years on the same battery. Note that a lot of that efficiency can really only be achieved in the analog domain. And a lot of people are exploring analog neuromorphics, but it has some significant challenges, which I'll also come back to. But nevertheless, and last but not least, there are 3 orders of magnitude in the digital domain. So there's still 1,000 times improvement in energy efficiency that can take your average cell phone from a usable time of 1 day to 3 years. So imagine 3 years between battery charges, or much more likely, imagine much smarter phones. To achieve that kind of efficiency improvement, using event-driven computing is critical. We can't waste energy when there's no computing to do. So to do that, we need new algorithms that work on events, and we need new hardware that is built to process those events natively. In short, we need neuromorphic algorithms and hardware. So that then is the core motivation for working with neuromorphics. But where did it all start? And it all started here. I suspect many of you might recognize this guy. He's a legend in the field. In fact, seldom is a field so defined by one person. But in this case, all neuromorphic roads lead to Carver Mead. Whether you look at the neuromorphic technologies that are already around us, and these are perhaps a little bit more prevalent than you might realize. The first trackballs, for instance, were based on the Fly visual system. The iPhone's really good noise suppression came from a neuromorphic startup connected to Carver's lab. The haptic sensors in many modern laptops also come straight from one of Carver's companies. All of these lead back to Carver. Or if you just look at the field, it's filled with Carver's students. When I first got into neuromorphics myself about 10 years ago, I kind of felt like I was the only person not from his lab. Of course, the field is much more diverse now, but his impact as an academic mentor remains extremely clear. Or if you look at the companies that he helped found, Actel and Impinj are worth a combined $1 billion. Or maybe most famously, Synaptics. Synaptics has shipped over 6 billion devices and has 2,000 patents and a runway of over $1 billion a year. And this is just scraping the surface. I've actually left examples of every category off just to let it fit on one slide. his impact has been immense. He's a legend largely because in 1980, he, along with Conway, wrote a book called Introduction to VLSI Systems. And then maybe more importantly, he wrote another book in 1989 called Analog VLSI Implementation of Neural Systems. And in that book, he described how he used the methods from the first book to create the very first artificial cochlea and retina chips. So here's a depiction of an artificial retina, which is also called a spiking camera or a dynamic vision sensor or an event-based camera. And there are lots of versions of this now, including what you might call the standard Davis camera from Innovision. There's also more recent cameras from from Prophecy. So their camera is called the Onboard, and Samsung also has a DVS camera. Now, all of these cameras share several properties. The main one being that instead of sending frames, spikes or events are sent. So these spikes indicate the location that a pixel changed from light to dark or vice versa. And these events can be used as input to neural networks to perform all kinds of image processing. Because the spike time that is generated isn't locked to a frame, it's extremely useful to visualize the output of these kinds of cameras as a 3D volume, as I've got down here on the bottom left. Two of the dimensions are space, corresponding to the camera's image sensor, and then the third dimension, in this case going up and down, is time. All of the spikes that you see generated here are an example of what would happen if you showed a rotating disk with a black dot on it. And so the black dot is generating the dense spikes, and all the rest is kind of noise around the edge. For something sort of different, we can also look at a spiking cochlea. So you have an input sound, it's filtered. That input is then integrated, and you get a spike once that integration passes some threshold. So you get a set of events that is effectively proportional to the power at various filter frequencies. And what we're seeing here is an example of the kind of spiking output you'd get for the words 4, or rather 5, 4, and 7. So what these kinds of sensors have in common, that is both the cochlea and the retina, is that they show some very significant advantages in terms of power, dynamic range, and latency. For instance, in the case of the camera, you send a lot less data because you don't actually send frames. You only send information when a pixel changes its intensity. And so this saves a lot of power. You can just imagine if you took the camera and pointed it like a security camera watching some space that people might be moving through, it essentially sends no information until something's changed. So if a person suddenly moves through the scene, then you only get spikes where that person is moving. The high dynamic range of such a camera means that it's very sensitive, so it works extremely well in very, very low light. And that's let people actually point these cameras at the sky and see satellites during the day. So the tiny little changes in fluctuation in light intensity caused by a satellite moving through the sky during the day can be picked up by these cameras. And last, extreme low latency means that the camera can provide updated information about the visual world every microsecond. So this gives a ridiculously high effective frame rate that can usually only be found in extremely expensive cameras. So I'm not going to bore you with more details about these specific sensors, but suffice it to say that these and others have demonstrated the importance of events-based processing by showing some very impressive advantages. So let's move up to the 2000s. And what you notice is that there's kind of an increase in attempts to build more cortically inspired neuromorphic computers. So this seems like a fairly natural progression, going from sensory systems, which collect and provide data about the world to the brain, to systems that process that information sort of more like cortex in order to determine what structure is actually in that sensory input, like maybe a vehicle coming towards you. And then, of course, that structure can be used to make decisions. So here are two notable examples of this kind of work. One is NeuroGrid, and the other is Spinnaker. So NeuroGrid is a project that's out of Kwabena Boahen's lab at Stanford University. And this is an analog digital hybrid design, in fact. So it sort of keeps the analog roots from Carver and incorporates about 16 chips onto a single board. And Kwabena is actually a student of Carver's. And together, these chips, those 16 chips, implement about 1 million neurons and upwards of 6 billion synapses. It's those analog synapses which really perform the computations, and they're extremely efficient, which is why you have such low power. However, the connections between the chips, or even between populations of neurons on the chips, are what they call soft wired. And that means that you can route different spikes to different sets of neurons, but you can't really change the weighting. And as well, the wire connects something more like areas together. So it's not really as fine-grained of a connectivity matrix as you would usually expect in a neural network. But of course, it has these extremely good power numbers. So it's kind of interesting to compare this to Spinnaker, which is from Steve Ferber's lab at Manchester University. Spinnaker is a more conventional digital system, and it's built out of low-power ARM processors, 968s. And in fact, Steve was one of the very first designers of the ARM processor. Spinnaker actually has a lot of these processors. So specifically, it has 18 of those cores on each chip. It has 48 chips on each board, and they have put up to 100 boards in a rack. And they have now put a bunch of these racks together, and recently this machine has been scaled up to 1 million cores. And that happened in 2018, which is getting a little bit ahead of myself here on the timeline. But in any case, this can run about 1 billion neurons. However, the power budget is much higher. It's about 100 kilowatts. So unlike NeuroGrid, Spinnaker has more typical synapses and weights, but it's still event-based. Because it has these more typical synapses and weights, it's also a little bit more conventionally programmable. So in short, it uses more power, but it's kind of more practical for AI applications. In both of these cases, the approach taken by each group was kind of a sort of build it and they will come. So let's make these really cool computers and people will figure out how to use them. So there wasn't a ton of consideration for specific algorithms. And as a result of that, there are some somewhat restrictive choices that were made in this these hardware designs. So the soft wiring in NeuroGrid, for instance, and to a lesser extent, the expected spiking rates on Spinnaker. So how quickly each neuron can spike. These two systems have clearly pushed the boundaries of neuromorphics. So let me turn to the last era in this quick history. So this is 2015 to the present day. So since 2015, there has been an explosion of activity in the area, especially in the context of commercially directed development. Some of this work has been a second generation of hardware, such as Spinnaker 2 or Braindrop. Braindrop was based on NeuroGrid. Other work has been new entries from large companies, such as IBM's True North chips or Intel's Loihi. And there's also been a number of startup companies, including BrainTrip, which has released the Akita, SynSense, which was formerly called AI Cortex, and then Gray Matter Labs. All of these have built their own hardware, and they're all leveraging neuromorphic techniques. Critically, there has also been important work on the algorithmic side. And a lot of that algorithmic work has actually been directly targeted by some of these hardware offerings. And this closer link between algorithm and hardware design seems to be quite beneficial for the field, and it's an ongoing process. So some examples of these new algorithms, we've got some which are focused on improving learning for spiking neural networks. So there are algorithms such as EPROP and Slayer and feedback alignment. They can all work in that way. There are other methods that have really focused more on learning offline and then mapping the result of that learning back into a spiking network. However, this only seems to work very well for feed-forward networks. And because of that limitation, there's also been other algorithms which are focused on robust and accurate processing of temporal data in recurrent spiking networks. In short, you can't easily port standard algorithms, recurrent algorithms like LSTMs and GRUs onto event-driven hardware. And so people have come up with novel methods like the Legendre Memory Unit, LMU, or the LSNN. And these have been proposed to essentially fill that gap. And interestingly, some of those proposals, like the LMU, for instance, has been shown to outperform the LSTM even in the non-spiking domains as well. So we see this cross-fertilization between spiking and non-spiking algorithms. And finally, there have also been algorithms invented, like temporal dithering, that make it possible to temporally sparsify networks. So this is analogous to weight sparsification, but it happens over time. And this kind of sparsification can increase the power efficiency and also let you make non-spiking networks into spiking event-based implementations. In many ways, the focus in the last 5 years has been not only on developing the hardware and the algorithms, but it's really taking these, putting them together and try to scale things up from the early days of the smaller systems to much bigger, more interesting, and more powerful systems while still focusing on efficient processing. Some examples of these algorithms, as I just mentioned, there are some large standard feed-forward deep neural networks that have been implemented directly in the spiking domain. So for instance, researchers at Purdue recently demonstrated a 138 million parameter spiking network that's solving ImageNet with a similar accuracy to non-spiking networks. As well, the team at Intel showed Loihi solving a 1 million element database lookup problem. So they cast this as a k-nearest neighbor search and then ran it on their large hardware. And finally, perhaps the largest functional network to date has actually been one out of my lab called SPAWN. So at the University of Waterloo, we demonstrated this in 2018, and we simulated 6 million neurons and about 20 billion connections running this big model. And this model spawn solves vision problems, motor control, reasoning, decision-making, does instruction following, and it even does intelligence tests. And the reason I'm bringing up is because right now this is still the world's largest functional brain model, and it's fully spiking. And it also provides a kind of benchmark to see how efficient current hardware is compared to the brain. So as you might know, the brain uses about 20 watts of power, and it's running 80 billion neurons compared to Spawn's measly 6 million. So right now we're running Spawn on standard GPUs, unsurprisingly, and those GPUs burn about 250 watts of power, so almost 10 times more than the brain. So we can think about what it would mean to scale Spawn up. So if we scale it up from 6 million to 80 billion neurons, how much energy would it require? It would require about 1.21 gigawatts. Well, not exactly, but it's something in the gigawatt range. This is an enormous amount of power, equivalent to that produced by several large power plants. And clearly, this doesn't seem like a viable option for AI. So as I mentioned at the start, it's this kind of observation that gives a lot of motivation for pursuing the neuromorphic approach. So let me turn to the hardware and look at scaling there. My first example is BrainDrop, which my lab actually helped design, and it's a direct descendant of NeuroGrid. It's fully programmable, unlike NeuroGrid, and it can run all of the networks that were used to build Spawn. Although the final system isn't very large, the power numbers are quite impressive. If we scaled that system up to a Spawn-sized network, it would require only 38 kilowatts, which is still 3 orders of magnitude worse than the brain, but at least it's something you could power in a home, and it's 6 orders of magnitude better than GPUs. In contrast, Luihi and Spinnaker have actually been scaled up to very significant sizes in the last few years. Specifically, Luihi can now run 100 million neurons on their Pohiki Spring system, which is pictured here at the right. This system has 768 Luihi chips and all the necessary interconnect to let them talk to one another. Spinnaker, as I mentioned earlier, has actually also been scaled up, and it can run about 1 billion neurons since 2018. The second version, so Spinnaker 2, is aiming even higher and is expected to have about 10 billion neurons running. And it also will have better power consumption than its predecessor. Both of these systems seem to be about 3 orders of magnitude more efficient than GPUs, that is the Luihi and Spinnaker 2, which is fantastic, but of course, it does still leave us in the megawatt range for a full-scale brain implementation. But more than simply making things bigger, neuromorphic methods, both the hardware and the algorithms, have recently started demonstrating some interesting state-of-the-art performance on a number of benchmarks and commercially relevant applications. So here are 6 examples from ABR and from my lab. And there are tens, if not hundreds, of others from other labs around the world. But of course, these are the ones I know the best. So I am going to pick these and actually just focus on 3 examples to dive into a little bit more detail. So the first example is keyword spotting. You see at the top right here. This is a very important commercial application of AI. Keyword spotting is finding its way into pretty much every new mobile device and home appliance that you can imagine. And what we're showing here is that we're running a keyword spotter on Luihi, and it's much more efficient than commodity hardware, including edge-specific devices like the Movidius chips. So this is a really good comparison because it's very apples to apples. The data set's exactly the same, the network structure is exactly the same, the training time, all these things are identical across the pieces of hardware. The only real change is that one is spiking and the other isn't. So we can also look at a robotic control application. This is the one in the top middle. This actually has some industrial relevance because it's showing controlling a real robot arm. So this is actually running on a robot. And that robot is, or rather the controller, is automatically tuning itself to be more effective. So what this means commercially is that you can leave a robot in the field for longer because this adaptive controller can account for changes in the robot's performance due to wear and tear. So you have these changes in friction as you use the robot over time. And the adaptive controller will account for that friction. You don't need to send people out to manually retune the robots. You'll also notice that the Movidius chip is missing from this graph. And that's because, like most edge hardware, it doesn't actually support on-chip learning. So this is in the field on-chip learning. But Luihi does support that. And so it can actually significantly outperform GPUs while running a network that many kinds of edge hardware couldn't. So the final example I'm going to turn to here is at the bottom right. And this is really a purely algorithmic example. What this is showing is how an LMU compares to an LSTM running on the Quora question pairs dataset, or QQP. This dataset presents a natural language processing problem that requires the system to determine if two provided questions are the same or not. As you can see here, the LMU with its optimal temporal memory is outperforming the LSTM by a pretty good margin. But more than this, it's using 500 times fewer parameters to do so. So from a power and memory perspective, that's a huge savings. I'll also note that that result is not actually state of the art. So state of the art performers on the QPP task, or QQP task rather, are transformer networks. But the first transformer network that beats this LMU score, so that's a transformer that gets about 88% accuracy, uses 50,000 times more parameters. So obviously, that's not the kind of thing you can deploy at the edge. So the last 5 years have seen big strides in the size of neuromorphic systems, in their applications to early commercial problems, and in their demonstrated power efficiency on interesting inference problems. So what I'm going to do now is turn to the question of how these networks compare to non-neuromorphic systems, and also hazard a guess as to what we might expect over the next few years. So by this point, it might be kind of obvious how neuromorphic and non-neuromorphic approaches to neural networks relate to one another. So the similarities are kind of obvious. Both want to solve these interesting problems. Both are using neural networks. Both are focused on AI. And both rely on learning in order to build their networks. It's not too interesting what they share in common. Rather, it's the differences that are most intriguing. So what I've done here is broken the differences down into two categories: fundamental differences, and then differences which are more a matter of emphasis. So let me start with the fundamental ones. And in fact, I think there's exactly one fundamental difference. And unsurprisingly, it's the one that I introduced on my very first slide. That is, neuromorphic neurons process information as a function of time, and non-neuromorphic ones don't. So I'm going to talk about this a little bit more on the next slide. The other kind of differences are really more matters of emphasis. So for example, neuromorphic networks, because they focus on temporal processing and dynamics, tend to use more recurrence. And that introduces dynamics into networks at the sort of network level as opposed to the individual cell level. As well, there's also this historical link between neuromorphics and analog computing. So we saw it right in Carver's second book. Now, this isn't a fundamental link. It's really one of emphasis. So you do have fully neuromorphic systems that are analog and that are digital and that are hybrid analog and digital. The last one that is, again, more of an emphasis than anything is online learning. So that is also often embraced by neuromorphic hardware designers, a little bit more so than non-neuromorphic designers. And this is fairly consistent with a general focus on dynamics, because really you can think of online learning as a longer timescale dynamics in the network. So I'm going to now just quickly touch on these two kinds of difference in a little bit more detail, again, starting with the fundamental differences. So the way to be really explicit, to specify something which you might want to call a fundamental difference, is to write down an equation. But I've also been told many times that for every equation you put in a presentation, your audience decreases by half. So hopefully some of you will be left after I show you two equations momentarily. But really what I want to do is be clear about the basic computational element that changes when you go from standard artificial neural networks to neuromorphic ones. First, imagine you have a simple input. We've got x going into our neuron. I introduced a variable. You can tell an equation's coming up. So that input is just a signal that's increasing over time. And we can put this kind of input into either of our computational elements, either our neuromorphic or our non-neuromorphic computational element, or neuron. Right? And very different things happen when we put in the same input. So first, consider a normal artificial neural network neuron. Its response might look something like this. Here, the neuron has a threshold right at 0, so it responds to the input immediately. And here's the first equation, a equals f of x. It, unsurprisingly, says that the output of a neuron, that is a for activity, is some nonlinear function f of the input, x. That function f can take many forms in current neural networks, simple things like ReLUs and sigmoids, 10H, and so on, all the standards. And at any moment during this input, there's always going to be a number coming out of that neuron, a number between 0 and 1. And typically, it's expressed as an 8-bit value, 16-bit value, 30-bit value, something like that. Right? So none of this should be very surprising at all. But let's look at what happens when we put exactly the same input into a neuromorphic neuron. So here's a standard spiking neuron response to that input. You can see that the frequency of the spikes increases over time. So in some ways, it's responding kind of like the standard neuron. Something is going up. But in other ways, it's totally different because it's only ever putting out a 1 or a 0 at any moment in time. And that means there's a 1-bit value, which is much more efficient than what we saw for the artificial neural network neuron. As well, its response can only be written as a function of input and time, my second equation. You can't leave time out of the picture like we did before. You have to wait some length of time before you actually see the effects of the input. So clearly our equation is different, and it's exploring or explaining a different kind of process. This is why neuromorphic computing is full of vocabulary related to time, event-based, spiking, dynamic, temporal, and so on. This same vocabulary shows up a lot when we talk about the biological brain. So that's what I see as the fundamental difference between standard artificial neural networks and neuromorphic ones. But there's also a cluster of other neural network features and methods that tend to be uttered in the same breath as neuromorphic. So it's worth quickly looking at these again as well. Since the introduction of dynamics at the fundamental level is what distinguishes neuromorphics, it's not surprising that, algorithmically speaking, network-level dynamics is also a focus. As a result, time series processing is something that you really see show up in neuromorphics a lot. And while recurrent neural networks are not unfamiliar to artificial neural network researchers, feed-forward networks are really the bread and butter of that field. Even time series data like language is often processed in a feed-forward manner in networks like transformers. Of course, large resource penalties are sometimes being paid for such an approach. And that's something that neuromorphics also tends to pride itself on: efficiency. Low power, but high speed and high accuracy are the core target of neuromorphic approaches. This focus on time-varying data, and hence dynamic solutions to computational problems, lends a little bit more of an engineering or physics feel to neuromorphics than you also might find in standard ANN research. Of course, all of these fields are well represented in the neural network community in general, but there's some differences in the kinds of technical tools people are comfortable with between computer science and engineering. When it comes to RNNs, which everyone uses for time series processing, those from traditional artificial neural network background tend to assume discrete time and don't explicitly state how information is transmitted over time. And that's really, again, a difference between sort of physics engineering and computer science. But people from the sort of physics and engineering backgrounds tend to propose RNNs, which are really starting with continuous characterizations of time. And so you often get explicit differential equations, which then might be discretized in order to implement on digital hardware. But they sort of start from this continuous space. And that might seem like a minor difference, but it actually has resulted in some surprisingly different kinds of networks. And I think this is actually working in favor of neuromorphics. So turning to the hardware, where the field really grew up, we see a few other differences from traditional approaches. So most closely related to the fundamental difference is that the hardware is often spiking or event-based. It's not surprising. And this is because we know that to most efficiently implement a class of algorithms, like spiking algorithms, you probably want your computing substrate to match the assumptions of those algorithms. So while the fundamental difference that I talked about doesn't strictly require events, it's really what we tend to see in the biological brain, and it's also been used in neuromorphics to get significant efficiencies. And lastly, there is some tendency for the neuromorphic community to embrace analog hardware, partly because analog is so efficient, and partly because a lot of neural processing can really be understood as analog computing. However, the practical challenges of large-scale deployment of analog devices seems to have made digital neuromorphics a little bit more commercially attractive at present. So what do all of these differences and everything else I've talked about today tell us about the future of neuromorphics? I think there are both expected and surprising consequences of what I've sketched out. Some of the more expected conclusions are that neuromorphic hardware is going to continue to improve, it's going to continue to scale up, and it's going to continue to carve out an important role in the AI space. Neuromorphic techniques might be less far out in the future than many believed just a few years ago. And in fact, I'd go so far as to expect that a major commercial inroad will be had in the next 3 years from a neuromorphic hardware offering. In particular, one that is digital, implements temporal sparsity at a fundamental level, And it's probably going to happen in an area that requires dynamic time series kind of AI processing. And so I've listed what I think are 3 leading possibilities for doing that. Maybe the more surprising conclusion is that I think there's a fairly immediate future for neuromorphics. I really expect a neuromorphic algorithm to be running on non-neuromorphic hardware and have a significant commercial impact. So this kind of hybrid approach where you'd use something like temporal sparsity and these dynamic recurrent neural networks and implement those as well as you can on commodity hardware, it's been extremely promising over the last year. And it's beat several state-of-the-art benchmarks by a significant margin. So while the full potential of a neuromorphic approach requires the merging of the hardware and algorithmic advances I've talked about, I think commercial AI applications will leverage neuromorphic advantages right away. In any case, I see this grand history of neuromorphics as continuing unabated for the foreseeable future. It'll be interesting to me to see if neuromorphics remains its own recognizable subfield, or if the advantages I've talked about will kind of be absorbed by AI accelerators in general. As they say, only time will tell. Thanks for your time and attention.